Alright, welcome back everyone to part B here in section 1, limits, the numerical and graphical viewpoints. This time, we're going to do things with a little bit more rigor, and in order to do that we need to use some algebra. So let me explain, right? So last time, what we did was kind of wishy-washy, at least in my eyes. For instance here, 1.4, I wanted to know, evaluate the limit as x goes to 0 of this f of x, sine of x over x. And we said, well, it seems to be getting really, really close to 1, so we're going to guess that the limit's 1. But right, nothing says that it was going to that versus, 0.999995 or something like this. Or maybe it actually went to 2 and it took like a sudden jump or something like this. So, again, this is kind of wishy-washy here. And so in order to evaluate these things out with a little bit more rigor, we're going to have to use some algebra. So in order to kind of get into this algebraic mindset, we have a few theorems here that I want to go over with you, and then we can get into some real problems. So the first one here is some direct substitution property. So the claim is, in most cases, polynomials, rational functions, root functions, kind of a lot of functions that we know and love and are out there sort of deal, a lot of the time, so long as a is in the domain of your function, then the limit, I want blue. There we go. The limit as x approaches a of f of x is just equal to plugging in a everywhere you see an x. So that's going to be f of a. So let's do some quick mini examples here. So if I did the limit as x approaches 2 of the square root of x. So 2 is certainly in the domain of the square root function, and so this is just going to get closer and closer to the square root of 2. Likewise, if I did the limit as x approaches 5 of 1 over x, again, kind of the only problem point, the only thing that's not in the domain here is 0, right? Because then I'd be dividing by 0, that'd be a problem. But 5 is in the domain. It makes sense to plug in 5 everywhere you see an x. So therefore, this is just going to be 1/5. So this is the direct substitution property, which says that, hey, you can kind of substitute things in most of the time, so long as it's in the domain of the function. The second really useful property says that if f and g are equal most of the time, essentially whenever x is not equal to a, they are equal, then the claim is the limit as x goes to a of f of x will be the same as the limit as x goes to a of g of x. And so this is a fairly complicated statement, right? What does this actually mean? And basically all you need to think about it is that, well, it says cancellation. This means that you can cancel things and it doesn't doesn't change the limit. This will also give us the power to multiply 1 by 1 in clever ways. So let me show you really quick. Maybe if I did the limit as x goes to 2 of 3x minus 6 over x minus 2. So first of all, we ask, can I just use the direct substitution property? I really like that. Well, no, you can't, because if you just plugged in 2 everywhere you saw an x, well, you'd be dividing by 0, and that's a big problem. So that's why we need to use maybe this cancellation. So the claim is something actually cancels here. I'm going to factor out a 3. And when I factor out a 3 from the top, I'm going to have x minus 2. And on the bottom, I also have an x minus 2. So these things nicely cancel, and this just becomes the function 3. So now I can use the direct substitution property, right? There's no problem now plugging in a 2 everywhere I see an x. In fact, there are no more x's. So this limit is just going to be 3. So this is how you can use this cancellation property and kind of along with this direct substitution property in order to evaluate a lot of limits. Okay. So let's go ahead and try this out. Evaluate the limit if it exists. So this is the limit as x goes to 1 of this kind of crazy function here. So maybe the first thing I want to do is try, can I just plug in a 1 everywhere I see an x, right? Can I just use my direct substitution property? So if I plug a 1 everywhere I see an x, we can see the problem here is that when I take 1 squared and I subtract away 1, that means I'm going to be dividing by 0, so therefore it's not in the domain of the function, right? It doesn't make any sense to just plug in 1 everywhere I see an x, otherwise I'd have a 0 in the denominator. So I hope that I can use the cancellation property. So this is where, like I said, we need to use a little bit of algebra. And one of our main algebraic tricks is that we know how to factor things, right? So I'm going to go ahead and take this function, I'm going to factor it with the hope that, hey, maybe something will cancel. So if I factor the numerator, right, using my good algebra skills here, I hope I get x plus 3 times x minus 1. Go ahead and double check. If you FOIL that out, hopefully you get x squared plus 2x minus 3. Likewise, to factor the denominator, I can use this difference of squares thing to get x plus 1 times x minus 1. And now you can see, hey, something actually cancels here, right? Those x minus 1s actually cancel. So now, the question is, can I just use the direct substitution property now that I've canceled these things? And the answer is yes, because there's no problem now of just plugging in 1 everywhere you see an x, right? 1 is in the domain of this function. So if I plug in a 1 everywhere I see an x, I'm going to have 1 plus 3 over 1 plus 1. So that's going to be 4 over 2, which is the same thing as 2. Okay, so this is how we can use algebra to actually solve out these limit problems. Let me show you, though, how to verify in our calculator, right? Because anytime we're doing something algebraically, it'd be nice if we can verify in our calculator. So I went ahead, and before the video started, I went ahead and plotted a few things here. So here's our first function. You can see it's x squared plus 2x minus 3, all divided by x squared minus 1. So if I go to the graph here, it's kind of hard to see, and in fact I get usually quite fed up with these graphs. So in order to figure this out, to make sure that I agree with the answer of 2, I want to show you a little bit of a trick here. I'm going to use the table. Now again, if I just go to the table here, it's very possible this doesn't really help me figure out, okay, as I'm really, really close to 1, I guess, what is this close to? So I'm going to change the table set. So I'm going to do second window. And first of all, I want to start at 1. That's where I'm really interested about things. And then I'm going to change by a really, really small value. So I'm going to do 0.0001. So that's saying that I'm only changing by 1/10,000th, I guess. So now let me check out my table here. So at 1, there's an error, right? Because again, you can't plug in 1 everywhere you see an x. That's a problem. But now look, kind of everywhere around 1, you can see it's getting closer and closer to 2. In fact, right here at 1.0001, the calculator doesn't even know the difference, right? This has so many 0.9s that it just did a little bit of rounding, right? Because it only goes to like 4 decimal places. So it rounded to actually 2 right here. So it's getting very, very close to 2. So this is how we can use our calculator to check, right? And so the question is, again, if we can just use our calculator for this, why do we need to learn it? And the answer is, there are going to be situations coming up, especially as we're tackling this idea at slope at a point, where you cannot use your calculator to evaluate these things out. So there's just not a way. So we need to know these algebraic tricks to really succeed at those problems here later on. Let's try one more here. So first thing, can I just use direct substitution? Can I just plug in a 0 everywhere I see an h? And the answer is no, right? Because then I'd be dividing by 0, so that's a big problem. 0's not in the domain of this function, right? It doesn't make any sense to just plug in 0. So now, though, right? You can't factor this. I need some other sort of trick, some other algebraic trick to get things to cancel. And hopefully, anytime you see a square root, you have this algebraic trick way in the back of your mind called multiplying by a conjugate. It turns out this is actually used for things, right? So I want to multiply by a conjugate. So let's remind ourselves what that is. So this is all going to be set up the exact same. And I'm going to multiply by the conjugate. And so the conjugate here is the square root of 9 plus h plus 3, right? So you change that minus to a plus sign. And of course, if I multiply it by this on the top, I probably should also do it on the bottom. Otherwise, my answer will have changed significantly. This will just be wrong. So, yep, whenever I multiply, I also need to divide. So this is multiplying by 1, really, in just some clever way. So let's go ahead and now FOIL this all out and see that, hey, this actually does something for us. So the limit as h, oh, I don't know why I did that. All right, limit as h goes to 0, And okay, let me get out maybe a different color here. So firsts. So square root of 9 plus h times square root of 9 plus h. So that's going to be, well, square root of 9 plus h squared, so that's just going to be 9 plus h. All right, that's nice. How about the, let's do outers next. So it's going to be plus 3 root 9 plus h, right? Because that's 3 times my square root of 9 plus h. And then let's do my inners. So that's going to be negative 3 times the square root of 9 plus h. And then my lasts. So negative 3 times 3, so that's going to be negative 9. Alright, so that's all foiling out. We can see that actually this quantity right here and this quantity right here are essentially the exact same. They're just opposites, so they're going to cancel out. That's very nice. And another thing, we can see the 9 here and the 9 here cancel out, right? 9 minus 9. So all that's left in the numerator is just h. Now in the denominator, you can expand this out if you'd like, but the claim is you don't need to. It's actually better to write it as h times this nasty quantity, square root of 9 plus h plus 3. And let's rewrite this one more time. The claim is something now cancels, that we actually did something good. So, okay, we did all that subtraction and stuff canceled away, and all that's left in the numerator is h. All that's left in the denominator is this h times this messy quantity. So you can see there's both an h in the numerator and in the denominator, which means that these things canceled, and all that's left is this 1, right? 1 is in the numerator. So this is now the limit as h goes to 0 of 1 divided by the square root of 9 plus h plus 3. And now the question, do you have any problem of just plugging in a 0 everywhere you see an h, right? Is that in the domain of the function? And the answer is now yes, right? Something canceled so that we could actually evaluate this out. So if I plug in a 0 everywhere I see an h, I'm going to have 1 over the square root of 9 plus 0, that's going to be 9, plus 3. So that's going to be 1 over the square root of 9 is 3, 3 plus 3 is 6. So the answer is 1/6. So if I was to go into my calculator here really quick to verify this, right, because that's a lot of work, I want to make sure that I didn't make a mistake with all this. So I'm going to be looking for 1/6, that's 0.1666 repeating essentially. So again, I went ahead and I plotted this. So I'm going to go ahead and turn that one off, turn this one on. And so my y2 value is the square root of, and now the calculator doesn't really graph with h's, right? It graphs with x's. So that's why I used x here. So the square root of 9 plus x minus 3 all over x. So again, if I went ahead and graph this, it's hard to really see what's going on here. So I'm going to do a table set and look at the table. So I'm interested around 0, and I want to look at very, very small values. So I'm going to do 0.001. So that way I get really close to 0. So now if I do my second graph to look at the table, you can see again at plugging in 0, there's an error. You can't do that. But you can look at what happens around 0. And you can see all around 0, we are very, very close to 0.1666. This says 7. This says 0.666. So you can see it's very, very close to 1/6, right? So that's how we can use algebra to actually solve for these limits exactly, right? And it's nice to always verify with our calculator. Okay, now that was kind of the most difficult part for here. The last stuff that we kind of go over in this section, I want to bring up kind of quickly, is this idea of limits to infinity. And these ones, there's not a lot of work to show. These ones, we want to use our calculators to evaluate out these limits for the most part. So this is the first one, the idea of the limits that we're going to infinity is that what happens if x goes to infinity, or x goes to negative infinity, right? So instead of going towards a finite number a, we could also head towards positive or negative infinity. So use our calculators to evaluate this out. So again, I'm going to get ready with maybe some equal sign here. So let's go ahead and graph this thing together with our calculator. Oops, not that one. Go away. There we go. All right, so I'm going to do y equals, and I'm going to clear out a few of these now that we're all set with them. And I'm going to graph x divided by e to the x power. And again, the graph's nice and everything, but I'm going to use the table. I think the table really helps with these things. So in this case, I want to get to very, very big numbers and very, very small numbers. So what I'm going to do is that I'm going to make my change in values very, very large. So I'm going to start at 0, but then I'm going to change by units of 10,000, right? So let's do second and table. So we can see I do 0, and then I do at 1,000, there's already an error, right? Or at 10,000, there's already an error. So this is saying this is way too large for me to calculate. So our calculator does have limitations. What about in the other direction? Oh, it also has error. That's nice to know. Well, let's change this then. Let's do, instead of start at 0 still, and let's maybe jump by units of 1,000, right? Hopefully that'll give us a good idea of what's going on here. So I'll do second table. Already an error, my goodness. All right, well, let's see what happens if I do units of 100. Second table. Oh, wow. So let's see what's going on here. It only does the first 100, 200, and then it starts erroring out. And you can see we have 4e to the negative 42. So that means there's 42 zeros, or I guess really 41 zeros, and then there's a 4. So this is a number that's very, very close to 0. And then in fact this one right here, it's 0.000000000, right? 84 zeros really, and then there's a 3. So this is extremely close to 0. So if I'm taking guesses, right, I'm saying that this is getting very, very close to 0. But our calculator kind of goes crazy after the first 100, 200, right? By 300, it's already gone crazy. What about in the other direction? Does it show me anything in the other direction? Negative 3, and then, oh, this is now e to the 4, right? E45, which means that it's multiplying by 10 to the 45th power. That means it's negative 3, and then with 45 zeros after that. So this is negative 3,0,0,0,0, right? More than negative 300 million or negative 300 billion or negative 300 trillion. This is with 45 zeros. This next one's with 89 zeros, and then it errors out. So let's maybe go back into the graph here, right? If I was just guessing based on this, I would say that this seems to be going towards negative infinity, right? This seems to be getting very, very small. Let's go ahead back to the graph here and kind of see if we can visualize this at all. So you can see, yes, as you go to the left, right, this graph seems to sink very, very quickly. It seems to be getting very, very negative very, very quickly, right? And likewise, as you go to the left, you can't really see it. It seems to be hugging this x-axis. It seems to be getting very, very close to it. The x-axis, of course, has the equation y equals 0, right? So this kind of confirms what our table was telling us. Okay. The other way we could talk about limits to infinity is that sometimes these limits don't exist in kind of an interesting way. So for instance, if I have this graph 1 over x, and I'm interested what happens as x gets close to 0, right? I can't plug in 0, then I'd be dividing by 0, that's a problem. But what happens if I get close to 0, but I'm writing to the left, right? So this is a one-sided limit with this little superscript with the negative sign. So I'm getting very, very close to 0. I'm writing the function and to the left of 0. Well, this to me looks like it's getting very, very close to negative infinity, right? This is just going to keep on sinking and sinking and sinking, getting very, very close to negative infinity. In the other direction, right, if maybe I'll use green, if I'm now bigger than 0, right, with the superscript with the plus sign, that means to the right of 0, or bigger than 0, then you can see that my function gets bigger and bigger and bigger and bigger and bigger, and it seems to be heading towards positive infinity, right? And now just to kind of bring this home again, right, so we have then what is the two-sided limit of f of x as we get closer and closer to 0? Well, these things don't agree, right? One's negative infinity, one's positive infinity, so the answer, just like it always has been, is does not exist. Let's try one more of these. This one, right, the graph's not given to you. So we need to use our calculator. Again, there's not a lot of work for these things. It's just interpreting our calculators and our graphs well. So what happens, right, as I get very, very close to 5, but I'm just a little bit less than 5, right? I'm to the left of 5. So let's go ahead and see here, and in order to solve this, I'm going to use the calculator, right? So I'm going to do y equals, and I'm going to graph 2 divided by, and then 5 minus x. And again, I can look at the graph of this thing, and we can see, actually this isn't so bad, right? As you get closer to, let's see, 5, and you're to the left of 5, you can actually see that it's getting bigger and bigger and bigger, and it seems to be going towards positive infinity. So let's write positive infinity here. Let's see, if you were bigger than 5, right? So I'm over here, I'm getting closer to 5, but from the right, it seems to be going down, down, down. It seems to be getting closer to negative infinity. Let's see if we can verify this, using our table. So I'm going to go ahead and use the table here. So I'm going to do a table set. I'm very interested about what's happening at 5. And I want to have small values here, so 0.001 maybe. And let's go ahead and look at our table. What's happening around 5? So yeah, you can see as it gets closer and closer to 5, it's getting bigger and bigger, right? So here was 666, 1,000, 2,000. So it's getting bigger and bigger. It seems to be heading towards positive infinity so long as you're a little bit left or a little bit smaller than 5. If you're a little bit bigger than 5, it seems to be heading towards negative infinity. So this is how we can use our table to verify this. So again, these two things do not agree, so therefore the two-sided limit does not exist, right? But a common misconception and kind of why I bring up this problem is some people think, oh, there's a negative sign here and a negative sign here, that these are somehow related. And so this example here shows that they are not related, right? So even with this negative sign here from the left, it does not go to negative infinity. These things actually do not correspond at all. So you really have to use the graph and figure these things out. You can't just say, oh, there's a negative here and therefore it goes to negative infinity. Oh, there's a positive here so it goes to positive infinity. No, again, here in the positive case, it actually went to negative infinity. So you really do need to work them out. The final case, both of these ones up here, you saw the two-sided limit does not exist. So this example right here is to show you that that doesn't always happen. So let me go ahead and, just like before, I'm going to graph this out. So I'm going to do y equals, and so on the top here I have, let's see, x minus 3, oops, not that, x minus 5. There we go. Close parentheses, divided by 3 minus x squared. And if I look at the graph now, you can see, right, we're interested about what's happening around 3. So around 3, we kind of lose the graph a little bit, but it seems to be sinking, right? It seems to be going either from the left or from the right. It seems to be going towards negative infinity. So my hypothesis right now, my guess is that in either case, as you approach from the left or the right, either way, they go towards negative infinity. Let's see if we can verify this with the table. So I'm going to go ahead and, again, I'm very interested around 3, and I'm going to do 0.0001, right? So baby steps here around 3. So let's go ahead and look at our table really quick. And so again, yeah, at 3 there's an error. Here you can see, okay, negative 1.5, and then there's 9 zeros after that. That's the E9 right there. So there's 9 zeros after that. I guess really you would move this decimal place over 9 times, so there'd be 8 zeros after that. So that's going to be a very, very negative number, right? Negative 1.5 billion or something like this, right? So very, very negative. How about on the other side? Likewise, negative 1.5, and then you move the decimal place over 9 times, so there's really 8 zeros there. So this is, again, a very, very negative number. So again, this is a way that we can use the table to kind of verify that, yes, negative infinity does seem to work out. So there are cases where the two-sided limit actually does not exist, right? So, I mean, we saw a couple times it does not exist, but sometimes you can actually have that either from the left or from the right, they agree that they're both getting smaller. So, that is enough, right? That's the end of 3.1. Like I said, this is kind of a big section, lots of topics, but we're going to be using this stuff to actually calculate out our instantaneous rate of change. All right, so I'll see you guys next time in 3.5.